This video is created by an advanced artificial intelligence. While we strive for accuracy, there may be some mistakes in the script or irrelevant media. If you spot any, we kindly ask for your understanding and encourage you to point them out in the comments section. We highly appreciate your engagement and feedback. If you find this video informative and engaging, please like it, subscribe to our channel, and share it with others who would find it interesting. Don't forget to click on the notification bell to stay updated with our latest content. Now let's dive straight into our topic. Picture a universe teeming with elements of unbelievable heaviness, challenging what we currently know about physics. These elements inhabit a world brimming with matter possessing unparalleled properties that could reshape our understanding of the cosmos. You are now entering the enigmatic domain of superheavy elements. Superheavy elements, or SHEs, are those chemical elements that have atomic numbers greater than 104. They dwell on the outskirts of the periodic table, a location where the laws of chemistry and physics seem to falter. The tremendous weight of these elements makes them highly unstable, often causing them to disintegrate in mere fractions of a second. The act of naming superheavy elements is a fascinating process steeped in scientific tradition. To understand superheavy elements, we first need to understand some key scientific terms. First, half-life. This is the time it takes for half the atoms in a radioactive substance to decay. For instance, if you have a kilogram of a radioactive element and its half-life is 1 year, after that year, you'd have half a kilogram left. Next, nanoseconds and milliseconds. These are units of time. A nanosecond is 1/1000th of a second, while a millisecond is 1,000th of a second. To put it into perspective, a blink of an eye takes about 300 milliseconds. Now let's dive into the superheavy elements, specifically those from element 116 to 121. Superheavy elements are those with an atomic number above 104. They're created in laboratories, not found naturally on Earth, and they have very short half-lives, often measured in milliseconds or even nanoseconds. Element 116, known as livermorium, was named after the Lawrence Livermore National Laboratory in California, a key player in its discovery. It has a half-life of milliseconds, making it highly unstable. The heaviest stable element that we know of is uranium. But elements heavier than uranium exist, they're just superheavy. Enter the realm of superheavy elements, those with atomic numbers ranging from 116 to 121. These are not your everyday elements. They don't naturally occur on Earth, but are rather created in labs by scientists who fuse lighter elements together. This fusion results in elements with incredibly high atomic numbers, hence the term superheavy. Let's take a moment to understand why these superheavy elements aren't naturally occurring. It's because they are intrinsically unstable. Their nuclei are so packed with protons and neutrons that they're on the verge of falling apart. This instability leads to a phenomenon known as radioactive decay, where the element spontaneously disintegrates, emitting radiation in the process. The time it takes for half the atoms in a sample of a radioactive element to decay is called its half-life. And these superheavy elements have incredibly short half-lives, some lasting only milliseconds or even nanoseconds. To put that in perspective, a millisecond is 1,000th of a second, and a nanosecond is 1/1000th of a second. That's faster than a blink of an eye. But here's a thought to ponder. Could these superheavy elements exist naturally somewhere else in the universe? It's a possibility. After all, the universe is vast, and conditions that seem extreme to us might be commonplace elsewhere. Perhaps in the heart of a dying star or amidst the catastrophic collision of neutron stars, these superheavy elements could form. Superheavy elements are not just heavier than other elements, they also have unique properties. Now, what makes these elements so special, you wonder? Let's dive in. Superheavy elements, those with atomic numbers from 116 to 121 and beyond, have a fascinating world of their own. They're like the high achievers of the periodic table, boasting properties that are out of this world, literally and figuratively. Let's talk about isotopes first. Superheavy elements have numerous isotopes, each with a different number of neutrons. This results in different versions of the same element, each with its own unique behavior and characteristics. It's like having a family reunion where everyone shares the same last name but has their own individual quirks. Now, onto stability. The heavier an element, the less stable it tends to be. Superheavy elements are no exception. They're more like shooting stars. They shine brightly but burn out quickly. This characteristic is measured by their half-life, a term that refers to the time it takes for half of a sample of a radioactive substance to decay. You might think of half-life in terms of seconds or minutes, but with superheavy elements we're talking about milliseconds or even nanoseconds. That's faster than the blink of an eye. Element 118, Oganesson, the heaviest we've ever created, has a half-life of less than a millisecond. Yet, despite their instability, superheavy elements are predicted to have some isotopes that could be relatively stable, thanks to a phenomenon known as the island of stability. This is a term used to describe a theory that suggests there might be a group of stable superheavy elements somewhere out there in the vast sea of the periodic table. Now, why don't these elements exist naturally on Earth? Simply put, they're just too heavy and unstable. But who knows? They might exist naturally in other parts of the universe. These unique properties make superheavy elements potentially very useful, but how can we use them? Let's keep exploring this fascinating world of superheavy elements. The potential uses of superheavy elements are as fascinating as the elements themselves. Let's delve into the world of superheavy elements, particularly those from element 116 to 121, and explore their potential applications. Imagine for a moment a world where we can harness the power of these superheavy elements. Their unique properties could open up a whole new realm of possibilities, especially in the field of energy production. For instance, these elements could offer a new and potentially more efficient source of nuclear energy. The energy produced from their decay could be harnessed and used to power everything from cities to spacecraft. However, the potential applications of superheavy elements don't stop at energy production. Their large atomic size and high electron count mean they could also have unique chemical properties that we can exploit. These could range from creating new materials with never-seen-before properties to catalyzing chemical reactions that are currently impossible with lighter elements. In the field of medicine, superheavy elements could also play a crucial role. Some isotopes of these elements could be used in medical imaging or even in targeted cancer treatments. In fact, the use of radioactive isotopes in medicine is not a new concept. For years we've been using isotopes like technetium-99 for medical imaging and radium-223 for treating cancer. But what about the presence of these elements beyond our planet? Well, it's not entirely impossible. Some theories suggest that superheavy elements might exist naturally in other parts of the universe or our galaxy. They could be formed in the extreme conditions of supernovae or neutron star collisions, although we haven't found any concrete evidence yet. The heaviest element that we've ever created is Oganesson, element 118. However, it doesn't exist naturally, and its half-life is less than a millisecond, which is a measure of the time it takes for half of the atoms in a sample to decay. The world of superheavy elements is full of mysteries and possibilities just waiting to be explored. The crown for the heaviest element we've ever created goes to Oganesson, element 118. Yes, that's right. Oganesson, named after the Russian physicist Yuri Oganesson, who made significant contributions to the field of superheavy elements. Oganesson is truly an element of intrigue. It's a superheavy element, and like its comrades in the periodic table, it does not exist naturally on Earth. This is due to its incredibly short half-life, a term referring to the time it takes for half of a sample of a radioactive substance to decay. For Oganesson, that half-life is less than a millisecond. In the blink of an eye, it's gone. But what does it mean when we say Oganesson decays? Well, decay is essentially a transformation. Oganesson, under the forces of its own instability, breaks down into lighter elements, releasing energy in the process. As for its properties, Oganesson belongs to the noble gases group, but it's a bit of an oddball. Unlike its group members, it's predicted to be a solid at room temperature, not a gas. This is due to its immense atomic mass causing a significant increase in attractive forces between its atoms. However, these are just predictions. The fleeting existence of Oganesson makes it extremely difficult to observe and confirm these properties. Now, you may be wondering, if it doesn't exist naturally, and its life is shorter than a heartbeat, what's the point? Well, the creation of superheavy elements like Oganesson helps us to refine our understanding of atomic theories and the forces that hold matter together. Even more exciting is the concept of the island of stability, a theoretical region where superheavy elements could have longer half-lives. If such an island exists, it could open up a world of new possibilities in science and technology. What about extraterrestrial environments? Could Oganesson exist there? Theoretically, yes. In the extreme conditions of a supernova, for example, the creation of superheavy elements is possible. But for now, that remains in the realm of speculation. From the mysteries of their existence to their intriguing properties and potential uses, superheavy elements truly push the boundaries of our scientific understanding. The exploration of superheavy elements doesn't stop here. The journey of discovery is far from over, and the future holds promising potential for new elements beyond the currently known 118. These new elements, starting from 119 and beyond, are uncharted territory, offering a world of potential for scientific exploration. The search for these super-heavy elements is a delicate dance of science, requiring precise techniques and advanced technology. The island of stability, a theoretical region where super-heavy elements could have longer half-lives, is one such area of interest. This term, half-life, refers to the time it takes for half of a given element's atoms to decay, often measured in nanoseconds or milliseconds for super-heavy elements. In the quest for element 116 to 121, scientists are not just seeking to fill the periodic table, but are also exploring their potential applications. These elements might have properties that could revolutionize fields like medicine, energy, or materials science. However, creating these elements and studying their properties is a complex task. Their high instability and quick decay rates make them challenging to work with. While element 118, Oganesson, is the heaviest element we have created, it does not exist naturally on Earth due to its short half-life. But the question remains, might these elements exist naturally elsewhere in the universe? It's a tantalizing possibility that drives the curiosity of scientists and researchers. The future of superheavy elements is a thrilling frontier, filled with challenges and opportunities. As we delve deeper into the heart of matter, we continue to push the boundaries of our understanding, unravel the mysteries of the universe, and challenge the limits of our knowledge. As we continue to explore the world of superheavy elements, who knows what fascinating discoveries await us?